Okay, I'm going to talk about my demo compiler. A lot of people just cannot believe that I wrote a compiler, a 20,000 line just-in-time, ahead-of-time compiler. I did some videos, 2 videos on my compiler. Now I'm going to talk about a mini compiler because it seems to blow people's minds that I wrote a compiler. So let's talk about this. We want to hand a buffer. We're going to hand a pointer to a character buffer, and this function is going to return a token. Now what a token is let's just imagine we're tokenizing this line right here. So we take I64, and I64 is a token. It's an identifier. The space is white space. We skip it. Lex is a token. The parenthesis is a token. U8 is a token. Star is a token. Star is a token. Underscore source is a token. Comma is a token. I64 is a token, star is a token, num is a token, parentheses is a token, brace is a token. This white space gets skipped. Then we get a U8 is a token, a star is a token. So tokenizing means converting to that. Now, this little compiler we are working on, let's go ahead and run it just to show you what it does. So we want to enter 1 plus 2 plus 3 times 4 plus 5. Okay, this is an integer expression compiler. Now, a compiler makes machine code. That's the difference in a compiler and an interpreter. This made machine code. You see these numbers over here? This column, that's machine code. Do you know what machine code is? 48 is the prefix for 64-bit instructions. So what's going on here? We're moving a constant 1 into RAX. We're pushing it on the stack. We're moving a constant 2 into RAX. We're pushing it on the stack. We're moving a constant 3 into RAX. We're pushing it on the stack. So we've done 3 integers. Now we're popping 2, adding them, and pushing the result. So pop 2, add, push result. Now we're pushing another 4 on the stack. Now we pop 2, multiply, and push the result. Now we pop 2, add, and push the result. Now we push 5, then we pop 2, add, push the result. And then the result for the expression is this pop RAX return. Okay, so this is a reverse Polish calculator. Okay, so we push 1, we push 2, push 3, then at this point we pop 2 and 3 and add them, and we push a 5, then we push 4, then we pop 2 and multiply, so we push a 20, then we pop. Okay, let's start over. So are you stupid or what? Okay, how hard is this? We have 1 on the stack, we have 1, 2 on the stack, we have 1, 2, 3 on the stack. We pop 2 and, no, what do we do? 1, 2, 3, pop 2 and add. So we take the top 2, add them. Then we have 1, 5, 4. Take the top 2, multiply. Then we have 21 on the stack. Okay, so now what don't you understand about machine code? This is the system stack that we're pushing on. Okay, so let's go ahead and let's jump ahead to so the Lex part gets a token. the compiler part puts the machine code into the buffer, the code buffer, into the code buffer. So here we have machine code. Do you see what machine code is? Do you see where it's, now that you know what we're talking about? Okay. So, Lex. So, if it gets a 0, that's not a 0. 0 is the end of the string. And if it's the end of the string, we return token end of file. If it's a space, a carriage return, or a new line, we advance the pointer, so we skip it. If it's a 0 to 9, then we multiply by 10 and add the number subtracted from subtracting 0. This is how you convert decimal to binary. So we're scanning in ASCII numbers, and then when we put it in the number, there's a parameter, there's an output that's number, and we put it in there, and we set the new source pointer because we advanced it, and then we return a token number. So the tokens we can get are end of file, number, operator, or left or right parenthesis. So these basically advance the pointer past the character, and it returns that new pointer. It resets that new pointer, and then it returns the token. Okay, so do you understand Lex? You understand Lex? Okay, it skips white space. It combines ASCII numbers into a single number, binary, and it returns a token. Okay, so let's go to the bottom. This is the main. We print our message. We get a string, and if the string is not the end, if it's not a 0 string, then we set a buffer, and we parse term. Okay, to start it, you parse a term, and then we parse until we parse will not end. If we get an error, we do a throw. That throws an exception. Then we unassemble so the user can see, and then we free the string and start over. Okay. So we parse term, and then we parse, and we're using a pointer to a character buffer as our source code, and our destination is for code. And then we execute the code. We unassemble the code, and then we execute the code, and the return value on the return value gets printed. Did you notice it prints the return value? So if I say 1 plus 2 times 2 plus 2 times 3, did you see down here it prints the answer as 13? So that this is executable machine code, and it makes an execution. So we're putting code into memory that was mallocated, and then we're calling that little subroutine that we compiled. Okay, so first we have to look at parse term and parse. Now the theory of parsing is LR parsing, recursive descent. Basically, if you have unary operators, this parse term would parse it. Like if you had -1, that would be a term. Now if you have student.name as a or student.age or student.score. Let's say if we had a real compiler and we had a structure, then this would be a term, this whole thing, because you can see how expressions work. So when you do modifiers, those are part of a single term. So you parse a term, and it turns out it's recursive indirectly. So we parse. Okay, basically all we have to do, let me just explain this. All we have to do is we tokenize, and when we get an operator, we check the previous operator. If it's higher, if the new operator is higher precedence, we execute immediately. So when we hit 2, okay, if we have parentheses, that's already taken care of. Two things can happen. Either you execute immediately or you postpone. Okay? That's all you have to know. You execute immediately or you postpone. Okay, I guess I should explain this. Now I have to think about it. Okay. So we're parsing a term. Now if you have a multiply, let's say we had 2 times 3 plus 4. I guess multiply is if it's greater than multiply and less than the new precedence. Greater than multiply and less than the new precedence. Greater than multiply and less than add. So as long as this is an add, or this is a multiply term. 2 times 3 is a multiply term. 2 times 3 plus 4 is an add term. The weakest precedent is either we keep going doing. Basically, you either do it right away or you postpone it, and just work it through. LR parser. So we're parsing, and when we're executing, that's when we're making code. So if you don't postpone it, you code it. So we're putting code, and that's how it works. It hurts my head at the moment, but anyway, LR parsing. I think that's left recursive. Anyway, just figure it out. So that's how it works. So I made a compiler. This malloc, now the question is this position independent? Well, hell yeah, it's position independent. Now what if we have what if we want to call print? How would we call, well, our print is at an address. If we unassemble address print, we get our print routine. So let's say we wanted to I could go ahead and do that. Do you want to modify it so that it does a print? I could do it if it entertains you. So we look in the symbol table. Let's see if we can identify C hash function star tempi H equals hash find. Atom is okay, hash find. So each task has a symbol table, and Atom is the father of all tasks. If it doesn't find it in the symbol table, it checks the parent. So it checks Atom. So we're looking for a string, needle string, haystack table, mask. So needle string is print. Haystack mask is the Atom task. Hash table. Mask. HTT function. Hash table type function. Okay, now we do a class rep. Let's just look at TempEH. I think we call it executable address, F9. Okay, so in the symbol table, it's a hash table. We have the address of the print function in memory. So if we wanted to call it, we could say call and then give that address if we gave the right parameters. Now maybe you want to know what a call is an E8 and then it's a relative offset. Okay, so if we wanted to call the print, then in our data table we would put E8 and then the current address, or the print address minus the current address, and that would be a call, and we'd have to deal with the stack. Okay, so do you understand how a compiler works? Do you understand how a just-in-time is easier than a ahead of time? For just-in-time, all you do, look up the instruction and then code a frickin' call. That's all you have to do, code a call. It's not hard. It's easy. Why don't you, as an exercise, I don't know, call some function in the mini compiler. Okay, so how hard can it be? So I have a single address map for all tasks. So all the code is at one location. What I mean is it never makes duplicate copies. The address maps never change. By the way, I use a 2 meg page table size, and I always map 128 gig, and there's just one map for all tasks on all cores, and an address is an address. And if you now you know how to let's say you wanted to figure out source debugging. Well, you would look in the hash table. I guess you have to search the whole thing to reverse the process. Going from a label to a number is easy. Going from a number to a label, you have to scan the whole thing. Anyway, you could make a structure for that, but okay, good enough.